All right, let's talk about the fundamental theorem of calculus. We first found antiderivatives, and then we found area under curves using rectangles and trapezoids. So what does an antiderivative have to do with the area under a curve, which we found using rectangles and trapezoids? Well, let's go back a bit. Maybe you should have studied sigma notation in probably an Algebra 2 or a pre-calculus class. Sigma notation looks like this. You've got your lower bound of 3, your upper bound of 6, and here's your expression, 1 plus k squared, and then this symbol sigma means sum, or add it all up. So you would plug in the 3 first, so you would have 1 plus 3 squared, and then you would plug in 4, so you go through the integers, 1 plus 4 squared, and then 5, 1 plus 5 squared, and then you work that out. That's going to be 10 plus 17 plus 26 plus 37, and that's going to end up being 90, okay? So that's sigma notation. You could use sigma notation to add up the areas of a bunch of rectangles. So here I have a graph, this function f of x is in blue, and then we're talking about having a bunch of rectangles, right? So like Riemann sums. And here I'm using the right-hand rule where the height of each rectangle is equal to the right evaluation point here. So you've got x sub 0, x sub 1, and the height of that first rectangle is equal to f of x sub 1. And the height of the second rectangle is equal to f of x sub 0. So the height of the nth rectangle is going to be f of x sub n. So this rectangle, of course, remember the delta x, that's going to be equal to the width of the rectangle. So the first rectangle, the height of it would be, so this first rectangle, the area of it would be delta x, that's the width of the rectangle, times f of x sub 1, that's the height of the rectangle. And the second rectangle, the area would be delta x, because remember they all have the same width, times f of x sub 2. And so on and so forth until you're at your final rectangle whose width is delta x and whose height is f of x sub n. You could condense all of this into using sigma notation. You can say, well, when k is equal to 1 up to n, you're just going to do f of x sub k times delta x, where f of x sub k, that's going to be your height of each rectangle, delta x is the width of each rectangle, and then n, of course, is your number of rectangles. This, of course, is still going to be an approximated area, not a true area. So to get a more precise value for the true area, we need to have more rectangles and we need to make them narrower. In other words, we need to make n very large. So you may recall that to make n very large, you can use a limit. So you can do the limit as n approaches infinity of the sum from k equals 1 to n of x sub k times delta x, and that will give you the true area. Now, you can imagine that this process can be quite tedious to do the limit of a summation. Well, there was a very smart bloke named Isaac Newton. You've probably heard of him. He was born in the 17th century. And one day in his lunch break, he figured out that there was a relationship between accumulating the area of these rectangles and the antiderivative. And he therefore adjusted the notation. So this limit as n approaches infinity of this summation became this notation. So this is where you got your elongated s that we talked about when we learned antiderivatives. Your lower bound is a, your upper bound is b. This formula is so precise, so this formula here with the limit of the sum is so precise that it gets its own symbol. Now again, f of x, that's going to be the height of each rectangle. So we're not using a subscript anymore. We're just going to call it f of x. That's the height of the rectangle. And then the delta x became dx as the width of each rectangle. Isn't that amazing? All right, let's see this magic in action. So what I have here is the graph y equals x squared. Over here, we want to find the true area between x equals 1 and x equals 3. So you'll recall that you can write that as the integral from 1 to 3 of x squared dx. You should also recall that the antiderivative is x cubed over 3. Now you don't have to put on the plus c, but I'll do that just to show you, just to make a point here. So what I'm going to do is write down the antiderivative, x cubed over 3 plus c. Like I said, you're going to see in a second, that's not required. And then I'm going to do a closed square bracket and write my boundaries from 1 to 3. Then in the next line, I'm going to plug in the upper boundary, and then I'm going to plug in the lower boundary, and I'm going to subtract. So if I plug in the upper boundary, that's going to be 3 cubed over 3 plus c. Then in the lower boundary, plugging in the lower boundary, I'm going to have 1 cubed over 3 plus c, and I'm going to subtract. Put some parentheses here. Now remember, c just represents some constants. I have 27 over 3 plus c minus 1 over 3 minus c, because I distributed that negative. And you can see that the plus c and the minus c, those are going to disappear. They'll just become 0. And then 27 over 3 minus 1 over 3 becomes 26 over 3. So 26 over 3, or 26 thirds, that is the true area under the curve from 1 to 3, which is kind of crazy. To show you that I'm not pulling your leg, let's do one that we can verify with geometry. We're going to do the integral from 0 to 3 of just 2x dx. So y equals 2x, of course, that's a line whose y-intercept is 0 and whose slope is 2. You can see that line right there. And we're bounded from 0 to 3. So you can see that when you drop that boundary in and shade it in, you just have a triangle. So if I'm going to do this first by finding the antiderivative of 2x is just x squared. And then I'll do a closed square bracket and put my boundaries over here. Again, you can put in the plus c if you want, but you don't need to because it's just going to become 0. Here's constants. Now, in the next line, I'm going to plug in the upper boundary. So that's 3 squared. And I'll plug in the lower boundary, 0 squared, and I'll subtract. And that's going to easily work out to be 9. Now let's verify this with geometry. So I said already that we can see that this is a triangle. So the area of a triangle is 1/2 times the base times the height. So that's going to be 1/2 times the base, which is 3, and the height, which is 6. Lo and behold, that is equal to 9. So this is, in fact, the process that's known as the fundamental theorem of calculus. The fundamental theorem of calculus works if you have a continuous function, and that function has an antiderivative over this interval from a to b. So the integral from a to b of f of x dx is going to be the antiderivative from a to b. So it's just going to be the antiderivative of b minus the antiderivative of a. So this results in the total signed area between the graph and the x-axis over the interval from a to b. Now, when I say total signed area, meaning that the area that's below the x-axis, that's a negative area, and the area above the x-axis is a positive area. So it's possible that when you do the fundamental theorem of calculus, you could end up with a negative result. You could end up with 0. So let's practice. Example number 1. We're first going to find the antiderivative. So the antiderivative of 3 would be 3x. And then, of course, remember, this is x to the 1/2 power. So the antiderivative there is going to be x to the 3/2 power divided by 3/2. Close the square bracket, 1 to 16. We can make that a little bit prettier. So that's going to be 3x minus, divided by 3/2, is multiplied by 2/3, x to the 3/2 from 1 to 16. We plug in the upper boundary, plug in the lower boundary, okay, and we'll evaluate those and subtract. Now here, we have to do 16 to the 3/2 power. Remember, that's really equal to the square root of 16 cubed. And of course, you're multiplying that by the 2/3. So the square root of 16 is 4 cubed. That's 64. So we have minus 2/3 times 64 over here. 3 times 1, of course, is 3. And then same kind of thing, we're going to have the square root of 1 cubed. Of course, that's just going to be 1. So it's going to be 3 minus 2/3. We got some fractions here. So let's get a common denominator. So that becomes 9 over 3, which is 3. So 3 is the true area under the curve from 1 to 16. Now, here's the same question on this slide. I'd like you to notice that here's your graph. This is the graph of 3 minus the square root of x. You'll notice it's a square root function, as you know, sort of like half of a sideways parabola, but it's like the bottom half of the sideways parabola because of that negative sign. And of course, it's got that vertical translation up to 3. You can see that this graph actually crosses the x-axis at x equals 9. So the area between 1 and 9 is positive, and then the area between 9 and 16 is negative. You could have, remember your properties of definite integrals, instead of going from 1 to 16, you could have separately gone from 1 to 9, and you would have gotten 20/3, and then gone from 9 to 16 and gotten negative 11/3, and then added them together. So that's one option that you could have done there. Now, in this example, we need to do a little bit of manipulation first before we can find the antiderivative. A lot of students ignore the fact that this is a quotient, and they want to just jump in and start using the power rule before taking care of the fraction first. But you cannot do that because there is no such thing as a quotient rule for integrals or antidifferentiation. So I'm going to split my fraction. I'm going to go from 1 to e of 4 over x plus 3x over x dx. I'll clean that up one more step, simplify that. That's 1 to e of 4 over x plus 3 dx. Now you'll notice here that I did not call this 4 times x to the negative 1. And that's because the power rule doesn't work for that, because you'd end up being adding 1, which would be 4 times x to the 0 over 0. We can't have that. But you should also recall that the antiderivative of 1 over x dx is equal to the natural log of the absolute value of x. So that's why I kept the 4 in the numerator and x in the denominator. So now I can do the antiderivative. We're going to have 4 times the natural log of the absolute value of x plus 3x, and we're going to evaluate that from 1 to e. Start by plugging in the upper boundary. So 4 times the natural log of e. I don't need the absolute value bars anymore because e is positive, plus 3 times e minus, let's do some extra brackets here, 4 times the natural log of 1 plus 3 times 1. So you'll recall that the natural log of e, that's just equal to 1. So here I have 4 times 1 plus 3e minus the natural log of 1, that's equal to 0. So this would be 4 times 0, and then minus, because I have to distribute that negative, minus 3. So I have 4 plus 3e minus 3, or 1 plus 3e. And so that is the exact value of the true area under this curve from 1 to e. Now, if you were to do this in your calculator, you'd get it approximately 9.155. On this slide, I'm showing you the graph of this function. This is the graph of 4 plus 3x all over x. You'll notice that this graph is not continuous over its whole domain, and that's okay. The discontinuity is at x equals 0. The section I was interested in is from 1 to e, so this is e over here, it's about 2.718, and the function is continuous within that interval. How would I know that this function is not continuous over its whole domain? Well, because it's a rational function, and you cannot have 0 in the denominator. So there's going to be a discontinuity at x equals 0. But I also knew that 0 was not in my interval from 1 to e. So it didn't matter that it wasn't continuous over the whole domain. It is continuous within the interval that I'm interested in. And that's what I got. I hope you enjoyed it.